So if it's like this, then I can now switch on, and 10 seconds later we will become fixed. Okay. So now we can really start with our class. As you know, these lessons are about electronic structure. Let me start by writing it down. So, having written down just the title reminds me of two comments I wanted to make. A, if you cannot read my handwriting, just tell me. Yeah? I don't get easily offended if you say this is unreadable and your letters are look like Chinese to me. Just tell me, I will try to write better. Second point is, if you do not understand what I say, also you can just interrupt me, I don't take offense. Because I know that I have this deficiency that sometimes I start speaking very quickly. When I start speaking very quickly, no matter what, okay? So just tell me if you don't understand what I say, and I will try to speak more slowly or whatever, okay? And also, again, so the biggest mistake you can do in the class is, not only in my classes, in any class, is not understanding and not telling that you don't understand, okay? So this is, I think, the most important thing. Okay, so now we will be talking about electronic structure. Any idea what this is? What are your expectations? Class on electronic structure. What do you think we will be doing? No idea? Just say me some keywords. What do you think will happen? Will we be talking about general relativity? Probably not. So what do you expect in a course on electronic structure?
Band structures?
You might expect band structures. Let's see. Just say bands. Okay. What else could you expect?
Materials?
Sorry?
Different materials.
Materials, perhaps? Other people have also an idea, or only you have an idea?
The relationship between the structure and the electronic?
Yeah, some relationship between electrons and matter, okay. One keyword which certainly you could say is quantum mechanics, no? Because, I mean, electrons and so on, they are certainly quantum objects, so we will be doing a lot of quantum mechanics. And you already see, in fact, here in these slides, I will show you in a minute, some orbitals and some stuff like this. So electronic structure is kind of all these, but there is one other keyword which is missing. Something which people like, when I was at your age, I hated it. Chemistry, exactly. So it is also something which is also inherently close to chemistry. Because, I mean, chemists are doing this. This is what they are wondering, what are orbitals around some atoms, how are the molecules, what is the structure, what do the electrons do. So we will, in this course, don't worry, nothing will stink and we will put stuff together, but we will be working in an area where also a lot of chemists are working, as you see here. Okay, so this will be a lesson where we are living on the borderline between physics and chemistry and biology and material science, all these kind of things. But so it will not be in the center of any of these things. For example, the center of material science. You have had in the first semester your course on solid state physics. That is really material science, and one did bands. Here we will not really talk about bands and so on, because this you have learned in solid state, what Bloch's theorem is. We will rather learn about methods, how one can calculate them, and how the electrons play into it. Materials, I've said. In biology also, I mean, biology is all about materials, and many biologists are doing electronic structure. So all these kind of things are important for what we will be doing. Okay? Now, I would like to start by giving you some motivation. And the motivation is the following. So perhaps some of you think rightfully that, well, this is all boring in electronic structure. Who would like to do something like this? But I would like to motivate you to show why, if you want to become a scientist, it is a good idea to be interested in electronic structure. So when you think about your future, you will be a great scientist. What is measuring kind of in today's world how important the scientist is? So when you apply to become a professor at a university, what decides if you get the position or someone else? Well, there are many factors, but one of the factors is how good you are perceived to be a scientist. Okay? So according to you, what is determining how good? How do people who have to determine professorships and commissions, how do they determine if you are a good scientist or if you are a better scientist? It's not by grades. What is today one of the qualities?
Productivity.
It's productivity, a scientific and what kind of, how is this measured?
It also depends
In
on
publications, no? Yeah. So one thing is people will look at what you have published. So you do research, you find out something new, you publish it. But then many scientists have many papers. What gives to your publications an additional weight is how important these are. This is measured by citations. No? So you write something, and then if it's completely useless, no one will take notice of it. Then it is, if it's something very important, which brings forward the world of science, other people will cite it and they will write, oh, as already this person has found, and they cite your paper. The more cited, the more important. Okay? And there are many measures how for your scientific future these things are measured. Okay? So now let's have a look at which kind of are the most important works in physics. At least it's not what I want to show you. Why is it? Please, I opened the wrong side file, obviously. So you see, it's not so good to be always on YouTube when you're doing these mistakes. I thought it was here. At least it was here before. Okay, here. It's not open. So we have to pray to Microsoft to get this right. Postgraduate. So in the PDF version, which is not there, I had, before coming here, opened the PowerPoint. It was there. Here we go. And here it is. This is what I wanted to show you. Okay, so what, not me, but a friend of mine has done, he went to the American Physical Society's webpage. Okay, so at American Physical Society, they are publishing some of the most important journals where our papers go. So Physical Review Letters, there are many journals which they have. Okay, and he looked at all the papers they have published from 1893. So essentially since the beginning of modern science, he looked at the papers and he looked which are the most important ones, well, those which are cited the most, and he put in the first 22. Okay? So this is kind of the modern history of physical sciences. These are the most important publications. So this is a friend of mine who has done it. And what has he done then? Well, he put in red all those which have to do with electronic structure theory. And you see that from paper number 1, okay, which is the paper by Lee, Yang, and Parr, which is about correlation energies, which is used in density function theory. About number 2, which is one of the most used density functionals, and so on. So the first 16 papers, the most cited, they are all about electronic structure methods. So kind of, this shows you, this is not a little niche of the physical sciences, no. These are the most cited papers of all times in physics are about electronic structure. And you see then, you have to go down to paper number 22, for example, to find the paper by Bardeen, Cooper, and Schriff about the theory of superconductivity. So this is a Nobel Prize winning paper here, number 22, everyone has heard about, but there are essentially 20 papers, much more cited than this one, who are all about electronic structure. Most of the things which you see here written in these very highly cited papers, especially if you look, for example, paper number 10 from 1964, the inhomogeneous electron gas by Hohenberg and Kohn. This is the basis for density functional theory. Also this paper or this invention won a Nobel Prize in chemistry in this paper. Okay? So, and many other things like projectile blended wave method, ultrasoft superpotentials, many of the things which you find here are things which we will be talking about in these lessons. Okay? So this is, as I said, I've shown you these two slides only kind of to motivate you and tell you electronic structure is not a little niche of physics, it's kind of mainstream in the sense that some of the most important stuff is really done in electronic structure. Okay? So, and I will now try to explain to you what this is and what electronic structure is. So, when I say electronic structure, one of the keywords which no one said, but which you could also have mentioned, is the keyword computer. Because electronic structure theory is not something you can do with a sheet of paper. Okay, so you cannot do like, there are many areas of physics where you can do your science, you take a sheet of paper, a pen, and you write some equations and you find something new. Electronic structure is not like this. In electronic structure, we know the basic equations, we know all of them, but we cannot solve them exactly. And a big deal of my lessons today and the next lessons will be to show you how these equations look like and make you understand why they are so horribly difficult to solve, and then a kind of all various ways people have invented to solve these very difficult equations. But to solve them, not exactly, not analytically, how you can solve them on a computer. So when I was at your age, I always thought, okay, if you cannot solve an equation, you use a computer and you solve it. But I will show you that these equations are so, even though they look very easy, but the solution of them is so horribly complicated that even the best computers in the world have no chance of solving exactly those equations. And I will try to explain to you why it must be like this, why even a computer cannot solve them easily. And then out of this comes all this theory, which has all these papers which many people have cited, which are very important. Try to, how we can put our electrons into a computer and solve what is going on in the computer. Okay? So one thing is we need to do computer simulations in electron structure. There is no way, if you do not like computers, you cannot do as your scientific career, you cannot do electronic structure. So the computers are one important point. And then the other point is obviously atoms. Okay? Because if you have electrons, electrons normally do not swim around in free space. They live around atomic nuclei, and then they decide how the atoms interact and how they glue together, where they have bonds and so on. Okay? So, if you think about electronic structure, and if you want to go towards a computer to solve them, then there are essentially two ways of doing this. And the world of people doing atoms and molecules and materials on a computer, already the very first step is separated into two half worlds, which I will try to explain to you. So imagine that you have some atoms. Here's an atom, here, here. So some atoms, okay. Each one has some nuclear charge. Hydrogen will have one, and so on. So you have nuclear charges, and in between there's the number of electrons. And these electrons make the bondings and decide which forces act on our atoms. Okay? Now, in one kind of world, you put this into the computer, you say there is this kind of atom here, this kind of atom there, and so on, you decide which atom is where, and then you model this in the computer as if there were springs in between. So you link all these atoms with something which could look like a spring, but then it is more complicated because you can also add some terms which depend on the angles which may appear or which on complicated geometrical facts. But what you are doing is, in this first kind of world, you are taking away the electrons. You are not trying to model the electrons, you are modeling the effect which the electrons have on your system. By saying, okay, the electrons between one hydrogen and another hydrogen is that they want to be at this distance, and if you put the distance larger, then it will be like a spring. Okay? So people use kind of a classical model to model what is the role of the electrons. And these things here are called classical models, or classical simulations. Many people are doing this. And the other world, which tries to answer the same questions, so the other world also has the same kind of atoms which interact. But in the second world, one really tries to solve what our electrons are doing. So one really tries to understand, here might be a chemical bond, here might be a chemical bond, here, so. And one solves therefore for electronic clouds. So we have electrons explicitly. And these are obviously quantum simulations. So since our course is on electronic structure, it is clear in these lessons we will live on the right-hand side of the blackboard, not on the left-hand side. But so now if you imagine the scientific world, do you think more people are working on this way of solving the problem or on this way? What do you think? The scientific community, are there more people on the left or on the right? So in one case you solve the electron problem as we learned, and as you see many citations. On the left you do it classically. What do you think?
Probably the
You think on the right? Well, in this class we will be on the right, yes. But in the scientific community, what do you think? More on the left or more on the right? Well, if I insist like this, then obviously it's the vast majority of scientists are working with these so-called classical models. Now, one might ask why. Each one of these models have advantages and disadvantages. And let's kind of try to write down what the advantages and disadvantages are, and then we will understand why most scientists work on this side. Okay? So as we've said, it's classical, so there are no electrons. One models the effect of the electrons, as I said, with springs and angles and geometrical effects. Okay? And therefore, in this world here, the forces between atoms are parametrized. Okay? What do I mean with parametrized? It means that, for example, if I say the atoms interact with a spring, then this spring must have an equilibrium constant and a spring modulus, so a hardness. And this is a number which you have to invent in order to model how, for example, the two hydrogen atoms will interact. Okay? So you need to fix those parameters, like spring constant, like equilibrium distance, like some angle dependence. And these parameters you have to find them. I will say in a minute how we do. But the fact that you do not have electrons, this means your calculations are super cheap. You can imagine that if you have a set of springs, solving their equation of motion in a computer, this is really easy. And one can use this for large systems. You can treat large systems. So here you can easily have, I mean, these typically are from 10 to the 4 to 10 to the 6 as an order of magnitude atoms. What is bad about this here? So the good thing is you can treat very large systems. The downside is you have no chemistry. So you could say, okay, no, chemistry is also an upside, it's not a downside, because we do not want to be chemists. But no chemistry in my context means that you cannot simulate what happens if a bond breaks or not. You see, if between two atoms you decide that there's a spring, then these atoms will always stay close to each other. But in a real material system, for example, one thing which, for example, I'm working on is you take some surface and you try to split water into hydrogen and oxygen on the surface. But so the water comes, it's H2O. Afterwards, you want it to be H2, so you have to split the oxygen somehow from the hydrogen, as it happens. But if you have some springs there, you will never be able to do, for example, water splitting or any splitting. So no chemistry means you can, no bond breaking. No bond breaking or obviously bond formation. And the second world, the world of quantum simulations where we are, is precisely the opposite. So we have electrons are modeled. And if you model really what an electron does, we know this must be quantum mechanics. This world here, where you deal with electrons explicitly, sometimes are called ab initio. And sometimes they are called first principles. Simulations. So ab initio, it comes from Latin, it means from the beginning. Ab initio is from the beginning, and it means basically the same as first principles. The idea is precisely you do not have what we have here. You do not have parameters. You start from the beginning in the sense that you only need to know what is the charge of the nuclei, how many electrons are there, and you need to know the Schrödinger equation, and everything comes from there. Okay? You do not put in any preconceived idea, between hydrogens there's such a strong bond, between a hydrogen and carbon there's such a strong bond, a triple bond between carbons is different from that. You do not need to know this. You only know that there are electrons, and you need to know the Schrödinger equation, and you try to solve it. Okay? So this is why these things are called ab initio or first principle. And electrons are obviously. Now, since we do all this, you can imagine that this is on a computer generally expensive. When I say it's computationally expensive, I mean that we cannot do 1 million of atoms like we can do in a classical simulation. So here, a typical simulation will have, whatever written here, so it typically have 100 to 1,000 atoms. It depends on how strong your computer is and so on. If you have very good computers at your disposal, you can go to several thousands of atoms. Sometimes we also do calculations just with 20 atoms. It depends, but this is the order of magnitude. So it's never 10 to the 4th, 10 to the 5th, 10 to the 6th number of atoms like in a classical simulation. Also, if you want to include time, so you solve what the structure is, and then you go forward in time and look at the next moment in time, how will it change, and so on. The time scales you can reach here are picoseconds, nanoseconds. The time scales you can here can go up to milliseconds. So you see there are also orders of magnitude in system sizes and in time scales. So one can address two different regimes with the two kind of calculations. So here I should add no parameters. And now I go back to my question. In which of these two worlds more scientists are working? We see now, okay, the advantage here is huge systems, long time scales. Small systems, short time scales, but we are able to break bonds and find out about materials which no one knows yet anything. So the reason why so many more people are working here is because there's one area of science which is particularly important, where a huge scientific community is, where systems are typically much larger, where you need long time scales, and where bond breaking happens rarely. And this is an ideal case for the left. Which is this area of science? The that was not me, but which is this area of science? Large systems, rarely bond breaking happens, you need long time scales, and a lot of scientists are working there because it's very relevant. Biology, exactly. So it's not physics. In biology, you are treating with proteins. The proteins swim in water, so you need not only the protein, which are already tens of thousands of atoms easily, you have also the water around, which is important for how the protein folds. You're interested in free energies, you're interested in time scales, and with the bio thing, you're always living here. You cannot really do the whole protein for milliseconds and so on with an electronic structure theory. I mean, these two words don't exclude each other. Sometimes in biology you have bond breaking. You have, for example, you would like to study photosynthesis, then you have to do something in order to be able to model certain biological aspects with these methods. But the vast majority of biological approaches, and you have the course by Ali Hassan Ali about these things, are by biologists, and they're here to the left. And simply because there are so many, many more biologists at the universities than there are physicists or chemists, therefore there are many more scientists working in this area. Okay? So therefore also you remember this list I've shown you where it seemed that the most cited papers, they are all in electronic structure and not on this side. But the reason for this is these were the papers from the American Physical Society. Okay? And the American Physical Society are physicists who mainly work here, while the huge majority of people who work here are biologists. Okay? So when I say this here is the overwhelming majority of scientists working here, but this is not typically in the physics, it's in the biology community. So this is very interesting. I myself am also doing classical simulation, so there is not at all any depreciation of this, but these lessons here are about the right-hand side. Okay? So we would like to understand atoms interact, and so there is one other very interesting link between the two worlds. I mentioned here that you need to parametrize your interactions. No?
Yes.
So where do these numbers come from? So if you're a biologist, for example, okay, and you would like to model a protein where you have all these atoms and so on together. Now you need to know what is the typical distance between a nitrogen and a carbon. You need to know how does it vibrate, how does it interact with water. So you need these parameters. Any idea where they come from?
Experiments.
Exactly. You can do experiments. So you have X-ray diffraction, you get structures, you get vibrational data. You can get from experiments a lot of parameters. Or you do calculations. So you take a little piece of your large system, you calculate it ab initio, so without any experimental input, without any knowledge, and you find out, okay, the bond distance is this, and it vibrates like this, and so on, and from these simulations, you can extract those parameters. So there's also a very fertile interaction between the two worlds. So when I say the world is separated into two, there are bridges across. And one of the bridges is that these simulations are often used either to check if they are good enough or to derive parameters for this world. Okay? So really these two things often are, and if you decide later in your scientific career to work on atomistic simulations, you will often have to go from one side to the other. And so these parameters come particularly often from, not from experiments, but from calculations. Okay? So now we kind of understand what we want to do. Our problem is we have given nuclear coordinates, we know the charge is sitting there, we know the nuclei are very heavy, so they will be slow, and typically they will be classical, and we have the electrons around, and we have to solve the Schrödinger equation for the electrons. Okay? So let's try to find out which equations we have to solve. And I've already told you, the equations look easy, and the equations are easy. The solution to these equations is the problem which we have to face. Okay, so which equations do we have to solve? Which equations to solve? Okay. So the system we have is what I have drawn as a picture. Imagine we have N, capital N with an N, nuclei. Each nucleus has a mass Mi, and it has a charge. Obviously, charge is positive, so plus the nuclear quantum number of this element times electron mass. Electron charge. Okay? So we have n of them. Each one has a different mass. And mind you, even the lightest of all nuclei, which is hydrogen, which is just a proton, what is the proton mass with respect to the mass of an electron?
1837.
Sorry?
1837.
Exactly. So it's more than 1000. So you see, and this will be an important point, the mass of this nuclei, and this is why I use a capital letter M, is always much, much larger than what happens for the electrons. Because we have our system comprised of these, and then we have Ne electrons. Each one has the same mass, lowercase m, with a charge minus times E. And we have already established just now that for whatever nucleus you have, the mass of the nuclei is always much larger than the mass of the electrons. This will be very important for us later. So now, knowing what the problems are, we have to write down, well, we want to do quantum mechanics, so what do we write down as an equation? You have Schrödinger equation, and what is the most important part of the Schrödinger equation?
Potential.
I would say the Hamiltonian, no? So anyone who does quantum mechanics always writes down some Hamiltonian, which then one discovers that one cannot solve it. This is everyone who is doing quantum mechanics always do this. We write down some model for some, we have a Hamiltonian, and then one shows why it is unsolvable. So also here, so therefore we know what the Hamiltonian of this system is. Hamiltonian comprises the energy of our system, no? So which parts, so you have this system made out of these two kind of constituents, what will be part of the energy? You tell me. Kinetic energy of?
Electrons.
Of the electrons. So let me call this T. E is kinetic energy of the electrons. What else?
Potential energy between electrons and.
Yeah. Let's stick for the moment still with the kinetic energy. Kinetic energy of the nuclei, obviously. Now we come to the potential energies, which you have already mentioned. So, which kind of potential energies are there?
Between electrons and themselves. Nuclei.
Between electrons and nuclei, yes.
And nuclei.
Nuclei.
Electron.
And electron. So there are three kinds of potential energies. Are these energies positive or negative? So kinetic energy is obviously positive, we have no doubt about this. What about the interaction energies, the potential energies?
Nuclei, electron, positive, electron and nuclei.
Exactly, because the nuclei are always positively charged, they will always repel each other. Electrons will always repel each other. So these two energies clearly and without any doubt are positive interaction energies, but when they interact, they will attract each other, this will be negative. Okay? So W, nuclear, plus the interaction energy electron, plus the interaction energy electron. And that is all. And now we can obviously write this down exactly what it means. So the kinetic energy of, say, the electrons is sum I equals 1 to the number of electrons we have minus h bar square over 2m derivative with respect to the nuclear coordinate, to the electron coordinate number 1 squared. This you have seen many times. The same for the kinetic energy of the nuclei. You sum over all nuclei. Sum from 1 to n. H bar squared divided by 2, no, this I call capital I, gradient with respect to nuclear coordinate I squared. So notice that here I put a lowercase index. This means I would make the derivative of my complete wave function with respect to the coordinate of an electron, and here with respect to the coordinates of a nucleus I, which will be at a given position. Then we have the interaction energy between nuclei and nuclei. So this I write as plus 1/2 sum over I, how do you call I prime, or I and j. I make here a prime, and then I have Zi Cj t squared divided by the distance Ri minus Rj. So this is a simple Coulomb interaction. I put in a plus sign because we have just said this is repulsive, so the energy is going up. If two nuclei come very close to each other, this energy will become really large, so they are trying to push apart. These are the nuclear charges, and it's charge 1 times charge 2 divided by the distance. Why is the factor of 1/2?
Double count.
Exactly, to avoid the double counting, because writing it just like this, I would count the interaction between I and J and I, so I put 1/2 and put all things here. The prime here means the term I equals J is excluded from the sum, because obviously nuclear cannot have potential energy with itself. So the prime is a short way of writing I goes from 1 to n and J goes from 1 to n, but I must be different from J. Okay? So for the electrons it is pretty much the same, also repulsive, so I have plus 1/2 sum lowercase I, lowercase j, a prime. Here you have no c's, just e squared divided by Ri minus Rj. Part number 2. And now finally we obtain minus something which is attractive, sum over all electrons, sum over all nuclei, Zi e squared divided by the distance Ri minus capital R. Here obviously there is no factor 1/2 because one is the sum of all electrons, the other of all nuclei. So there is no double counting here, so no factor 1/2. Also no prime, because obviously, I mean, I illustrate, we have always one electron, one nucleus. So I promised you the equation would look quite easy, because the equation to solve is obviously this Hamiltonian H times some certainly complicated wave function is E0 times something. Okay? So all these courses and lessons are about solving the time-independent Schrödinger equation, finding the minimum energy of your wave function, the minimum energy E0, for a Hamiltonian, which is frankly an easy Hamiltonian. There's nothing complicated in this Hamiltonian, no? So, let's have a little look again at this Hamiltonian. So we have said, no, first, I always like making stupid questions. So we have said these terms are all positive except this. But if I look at the kinetic energy, this looks negative, no? There's a minus sign, and then these are all positive constants, and here I have a square. How come that there's a minus sign? Kinetic energy must be positive. What am I doing wrong? Why is this positive if there's a minus sign in front of something which is all positive?
No, it's
a stupid question, obviously.
So this is we are interested in the eigenvalue of this operator. This is just an operator. We have to calculate. That is the number that we want.
Yeah. So, but why is this positive definite? Can you see it quickly? Why this is positive definite, even though there's a minus and this all looks like squares? the operator is must be positive definite, otherwise it could not be kinetic energy. No, kinetic energy is always positive. Here's a minus sign, so this thing here must have a negative expectation value. Why?
Bounded. Because in an atom, say for the electrons, the bound states have negative energies.
Yeah, wait a minute. This is the complete thing value of kinetic energy plus potential energy, and the total energy is negative. What you're saying is that this E here is negative for a bound state. I completely agree. My question is only the kinetic energy. It's an operator, as you said. But this operator must be positive definite, otherwise it would not be kinetic energy.
So I think it's
Where it adds
something
to
with
is
hermeticity.
imaginary.
But can anyone apart from the two of you has an idea?
It adds on something imaginary.
No, the wave function can be imaginary, but it is not necessarily imaginary.
Actually, it's like...
Wait a minute, not you and not you. The others perhaps also have some idea. Anyone has an idea why this is always positive? Or what am I saying wrong when I say, look here, this here is all constants which are all positive. Here there's a square, but there's a minus in front of it. If one doesn't think, it looks disturbing, no? You see the problem? The problem is whenever you calculate an expectation value of this, with whatever wave function, it must always be positive if it's a kinetic energy. The answer is, this here is not a square, okay? It's not mass squared or something. This here is a derivative, a second derivative. It is not a square of something, okay? And if you take here any wave function, you calculate the second derivative and you multiply it with the wave function complex conjugate, is what you need to do. This is the same as if you would calculate, you can do an integration by parts. So it is minus the first derivative acting on the wave function, and you take this on the other side too. So it is minus times a square, which is positive. Together with this, it's always positive. Okay? So, just to say it again. So, this here is a second derivative acting on some wave function psi. Okay? So, in the end, to get the expectation value, we have to integrate this over all space. Okay? But if you integrate this, and then here on the left-hand side, you will have psi star. You can do an integration by parts, and the integration by parts gives you, apart from surface terms, which are 0, gives you gradient psi star times gradient psi. And now this is very obviously a number times its complex conjugate. This is always positive with the minus sign, and this minus sign, it's always positive. So it is, this way of writing the kinetic energy is obviously something which is positive there. I'm saying all these kind of stupid things because we will have to handle these complicated equations. And there will I will show you that a lot of trouble comes in. So we should really get first a feeling of what happens here, okay? So the kinetic energies are derivatives, second derivatives, and we know it's positive definite. Now it is all positive. I already anticipate it will be difficult to solve this equation. So one thing we could do is we could say, okay, let us neglect perhaps some terms in this equation. And the term which is obviously different from all the others is this one, because it's the only one which is clearly negative definite, it's attractive. So what would happen if someone had the bad idea to say, let us cancel this, okay? So let us not consider this term. What would happen if we neglect this term in the Hamiltonian? Well, a catastrophe would happen. This we can certainly not, because then you have a kinetic energy and a repulsive interaction between nuclei. You have a kinetic energy and repulsive interaction between electrons. Everything is repulsive, everything would fly apart. So if we try to describe a material with an equation where we neglect the last term, no way we could get this. Okay? Because everything would fall apart. What gives structure to materials and in fact to the whole universe, to everything, is this term because it attracts. Okay? So first thing we learn therefore, this here is important because it is needed to keep things together. The next question about this equation we should ask is, even if you are able to solve it exactly, is this an exact equation? So if I give you a miracle computer which has a miracle program inside it, which can solve H psi is epsilon psi for this Hamiltonian. Exactly. Imagine this is possible somehow. But would the answer be the exact solution of, say, a material, or is this even an approximation? So by writing this, my question is, writing down this Hamiltonian is an approximation, or writing down this Hamiltonian is exact?
Are we
Let's make a vote. Who thinks this is an approximation? 1, 2, 3. Yeah. And who thinks this Hamiltonian is exact? You. Okay, so we have a half-half. We are split in two. The answer is yes, we cannot solve it. But even if we could solve it, it is an approximation. And now, whoever says this is an approximation must tell me what is missing. Why is it an approximation? Something is missing. Or something is neglected. We did some assumption for writing down this Hamiltonian. You see, before embarking onto solving something complicated, which I tell you already, it will be complicated to solve it, we should know if at least we can then expect to get something exact back. And the answer is no. This is an approximation. What is it?
Spin relativity.
Spin, yeah, this is the key point. Relativity is missing. Okay? So this is all a classical Hamiltonian. Okay? It is, no, I should not say classical, it is with the quantum mechanics, it is a non-relativistic Hamiltonian. You see, we write the kinetic energy as h bar square over 2m second derivative. This is clearly Schrödinger equation, this is clearly non-relativistic. If you were here not in the diploma course on condensed matter, but in the condensed matter course on high energy physics, then probably you would immediately say, no, this is non-relativistic, we do not care, because in high energy, obviously all they do is care about relativity. So if we would have liked to write the exact equation for the same problem, we would not have had to write a Schrödinger equation, like this, with this Hamiltonian, but we would have had to write the Dirac equation. The Dirac equation and do relativistic quantum mechanics. Now, we are not going to do relativistic quantum mechanics for the good reason that most of condensed matter physics is non-relativistic. So the approximation which we do by writing this classical Hamiltonian, this non-relativistic Hamiltonian, is a very good approximation. But in which cases do you think it might fail? So when you start with something which is an approximation, you should always think about when will this approximation fail? Under which circumstances can I expect good answers from this? When will the non-relativistic approximation fail us? So when you think about, when you learn first about relativity and all these kind of things, relativity becomes important when something becomes really fast. No? So if something approaches the speed of light, better do relativistic physics. Now, when will anything approach speed of light in a given material? Certainly nuclei in a typical material, they sit there, as we said, they are very heavy, they move heavily around, they are not moving with the speed of light at all. So the nuclei are very often, not always, but often very well described with non-relativistic physics. The electrons is a different matter. The electrons, they are everywhere, they are these clouds of electrons, and what is their local kinetic energy is always, like it is in classical physics, the difference between the potential energy at that point in space and their energy. Okay? So in classical physics you have this picture that you have some potential energy mountains. A particle has some given energy, okay? And the potential energy is this and the kinetic energy is always this. So when the potential is steep, here you have a high kinetic energy, here you have a low kinetic energy. So if you're traveling with a bicycle in the mountains, you arrive very slowly on the top of the mountain, you're very fast in the bottom of the mountain. Now you're an electron, and what you see are Coulomb interactions with your nuclei. So you have your nuclei, the potential which you see is something which goes like this. Here it is attractive, this here is the minus c over the distance. Okay? The term which we have here. Okay? So you have something which is very attractive. Now, if the electron has this kinetic energy, if it is very close to the nucleus, and in fact is attracted to the nucleus, as we know, and when it comes very close to the nucleus, it will have a huge kinetic energy. Especially if the nucleus is a heavy one, then this number C here is large. So imagine this here might be 100 or so if you have a heavy atom. So then this potential is even deeper, and an electron which comes close to the nucleus will be very fast. It will be very fast, very close to the nucleus only, but it can happen. And therefore, you will need relativistic corrections, but they will happen only close to the nucleus. And there is one keyword which you have certainly heard in your course of quantum mechanics. Exactly, spin orbit coupling. So the reason that your electrons become quantum mechanical when they are very close to heavy nuclei, this gives rise to spin orbit interaction. You have calculated certainly spin orbit for the case of a hydrogen atom, which is the lightest one, and you have seen that it was really very small. You had to look very close into the line shapes of the absorption spectra, and then you could see the spin orbit terms there. So the relativity corrections are very weak for hydrogen, obviously. But if you do your calculations on uranium or on gold or something, then for electrons being close to the nucleus, this Hamiltonian is not good enough. But luckily, there are ways to correct this, but we must keep in mind, even if we solve this Schrödinger equation exactly, we will not be able to, but even if you could solve this exactly, we still would not have spin orbit coupling, or more generally, any relativistic effects close to the nucleus. Okay? So, solving this will be a challenge, it will be difficult, but if we do it, we still have no spin orbit coupling and other relativistic effects. And just one kind of an example of where these things are important. You all know gold, no? We all know gold is this nice yellow shining metal. And people have shown with calculations, so in an experiment there is no way to switch off in a real material relativity. In reality there's always relativity and you cannot switch it off. But in an ab initio computer simulation, you can solve the equations for gold with this Hamiltonian, with a purely non-relativistic Hamiltonian, or you solve the equations for gold, including relativistic corrections close to the nucleus. And in the case of gold, the interesting thing is, if gold would be a non-relativistic material, then it would not look like it looks. It would not be yellow, it would not be a noble metal, it would not look... So all these nice things we know about gold is, in fact, due to relativistic effects of electrons when they come close to the nucleus. This is something it was about 10-15 years ago, someone used the methods which we will learn how to use them for gold and switched on and off relativistic effects, and has shown that gold is what we all appreciate only because of the relativity close to the nucleus. Obviously, gold is not hydrogen. Gold is a heavy element. It has a huge number C, and therefore there are strong relativistic effects close to the nucleus. Another example for a prototypical heavy element is lead. No? Lead, we all know lead is heavy, and in fact, lead batteries, the ones which we have all in our cars to start the engines, one can also show that in fact lead batteries work only due to relativistic effects and which are induced by the very strong Coulomb potential on the electrons. So these relativistic effects, they are not just there like in a hydrogen atom spin orbit and you see little shift. They really can be determining features of materials properties. Okay? So when we now embark on solving this equation, keep in mind, yes, it's difficult, but even this result is not good enough to have everything. We have no relativity here, but it doesn't matter. Okay, so next question is, now we have an equation. Let's try to solve it. How would you go ahead of trying to solve this? You see, there are areas of physics where all the challenge is finding the right equations, and then once you have the equation which covers everything, the problem is considered solved. Here we know, apart from relativistic effects, here we know exactly the equation. We have a Hamiltonian, we've written it down, we know this is the equation to solve, HC is E psi, so all is clear. But now, how would you solve it? Any idea what is a way to solve such an equation?
I think in most of the cases in condensed matter, we would use an approximation that nucleus are heavy, so Born Oppenheimer to knock out the second term.
Okay, so yeah, this will obviously be what we do in the next lesson. We will do Born Oppenheimer, but before doing Born Oppenheimer, we will discover why it's necessary to do it. But first, what is a way to solve this equation? More generally than already saying which approximation we do. How do you solve? So I give you a Hamiltonian. I want to know from you as good approximation as possible to the energy, to the ground state energy. What would you do, or what should one do?
So if we don't know the exact solution, we try to use perturbation theory.
You could, but you see, perturbation theory is what you've learned in quantum mechanics. But perturbation theories, if you have one Hamiltonian of which you know the solution and then you change it a little bit, but here, where is the perturbation? I mean, these are all big terms. Kinetic energy is large, the Coulomb interactions, they are all large. There's not one term which is small with respect to the others. Perturbation theory is not our solution.
Stop to 8 minutes.
Sorry? Stop to?
8 minutes.
Yeah, I just said before, if we would eliminate something, it might perhaps be this term, but then everything flies apart. In fact, these terms are all large. We cannot do perturbation theory in that. We cannot just say we neglect one of them. So, but still, so I give you an equation, an Hamiltonian. I want to know I even do not want to know all solutions, only the lowest, the ground state, the lowest energy. What would you do? Well, as a matter of principle, what one needs to do is, one writes some kind of wave function, and one says that for this wave function, so the Hamiltonian I know, the wave function I must know, and so one can write, since we know the Hamiltonian exactly, one can write all the matrix elements of all these terms, and then one says this must be minimal. And if you minimize this quantity, then psi is the ground state energy, and E is of this psi 0, H psi 0. So one way of solving this complicated equation is writing some form of the wave function and then minimizing it. Okay? So the wave function is obviously a function. So obviously we need to do something with the wave function to solve this. So what can a wave function be? So the wave function psi is a wave function of nuclei and electrons. Okay? So our wave function will depend on the coordinates of each of the nuclei, where it is, and it will depend on the coordinates of all of the electrons. So we can say that here this complete wave function is a wave function of R1, R2, up to Rn nuclei, and then of electronic coordinates R1, R2, up to Rn electrons. So a wave function which depends on many coordinates. What we could now say, okay, if it would depend only on one coordinate, so in one dimension, we could say if we have to write psi, we choose some points in real space, and we store in the computer the value of the function at each of these points. Okay? And if we know this, we know the wave function, which is good. So we could now say we make a grid for each of these coordinates, so 3 x, y, z for the nucleus 1, 3 for the nucleus 2, and so we have 3 times the number of nuclei times 3 times plus 3 times the number of electrons, so many coordinates, and we solve, and this energy here depends on the values. We minimize it, and we are done. Okay? This would be one way of going ahead of solving the electronic structure problem. Would this be a way which is practical? Probably yes. Huh? So we have to solve the wave function anyway, but do you think that this would be right? So my question is, I give you this Hamiltonian, we write the total wave function as a function of the coordinates. We have to find out the value which the wave function has for all these coordinates. We minimize, and we find it out by minimizing this quantity. It is a clear prescribed, I mean, it might be complicated, you might need a lot of memory in the computer, but it is a well-described approach. No? But if you do this, do you think you would get a right result, or have we been missing something?
The wave function is not exact.
Well, it would be as exact as we made this grid finite as if we describe it. Okay, so this is not so much the issue. But there is a problem of principle. Can we just use any function of all these coordinates and find the one which minimizes the energy?
So
Are we allowed to do this?
Normalization.
Sorry?
Normalization.
Yeah, then obviously we would look for a wave function which is such that norm square is 1 if you integrate over all space. This we can do without problem.
How do we deduce the form of the wave function in the first place?
No, the shape comes out by minimizing the energy. You try many shapes, and the shape which minimizes the energy is the shape of the ground state. No? This is precisely my suggestion to you. What is wrong in this? I mean, it would be wrong. Doing this, you would find out a non-valid wave function. What have we been forgetting? Think about your classes in quantum mechanics. In quantum mechanics, you have solved harmonic oscillators, you have solved the hydrogen atom, you have done perturbations about this. But then later on, you learned, I think at least here, if not in the second semester, in the many body classes, you have heard something what happens if particles are identical. No?
Yeah.
So, we have forgotten one little detail. We have all these quantum particles, but the electrons are all identical fermions. So are the nuclei. So not any wave function is an allowed wave function for identical particles. No? This is why. They must be symmetrized in the right way. The nuclei depends if they are fermions or bosons, but they must certainly obey the right symmetry relations. For the electrons, they are all fermions. They must all supply. So, for example, if we take our solution wave function, it must be such that if I exchange the coordinates of two electrons, I must get the same wave function with a minus sign. Remember, this is what is the rule for fermions. And if we just minimize everything, I can already tell you what we would find is a wave function which is a bosonic wave function because all electrons would go to the same state. So the Pauli principle and more generally the right symmetry with respect to exchange must also be employed. And this is the real heart of the problem which we have at hand. We could in principle just minimize this quantity because we know the Hamiltonian, we know the wave function, but we cannot just minimize it with respect to any function of 3 times 2 n coordinates. No way, because the wave function must also satisfy the symmetry properties. It would be very unphysical if we find as an electronic wave function a bosonic wave function. It cannot be. They are fermions. They must have the antisymmetry when you exchange them. So we must minimize the energy. But we are allowed to consider here for the wave functions only symmetry allowed wave functions. And this is, you will see later, this is what makes everything so complicated. Okay? So this is why we cannot just start a computer and sit there and minimize the Hamiltonian between. Okay? So this is, in a nutshell, the difficulty of what we will try to solve in these electronic structure courses is that we have an easy Hamiltonian. We in principle know what we need to do, minimize the energy, but we are hindered by the fact that our wave function must satisfy fermionic properties for the electrons and for the nuclei also if they are identical, the right exchange properties. If the nuclei are fermions or bosons depends obviously on their quantum numbers. Okay? So we have to go one step back and wonder a little bit how will the solutions look like, because we should do some more approximations. Now we come to the one Oppenheimer which you have already mentioned. Can I cancel the blackboard? Okay, so you now know the Hamiltonian. So we will have to satisfy this, I call it symmetry. Symmetries is on one hand kind of a geometrical symmetry. If the molecule, for example, has a symmetry, a mirror symmetry in the middle and so on, these are symmetries, but I call also a symmetry with respect to exchange. Exchange electron 1 with electron 5 is also a symmetry. So when I say symmetry, I do not only mean space symmetry, but I mean also these exchange symmetries. And I've already said, so the symmetries will be a source of our headache. And moreover, this headache is different for the nuclei than it's for the electrons. So let us have a look if we can at least get the problem a little bit easier by looking at electrons and nuclei separately. Okay? So by decoupling them. And how could we kind of to do this? Okay? And for this I always like making very easy comparisons and very easy stuff. So I will now make two completely trivial comments. Okay? So comment number one, and then if we take these two trivial things together, it will be useful for us. So trivial comment number one is the role of the kinetic energy. We have seen that in our Hamiltonian, both for the nuclei and for the electrons, we have a kinetic energy plus a potential energy, and then the mixture. Okay? So, if you look, for example, at the easiest case you've seen, a simple harmonic oscillator. You have solved the harmonic oscillator many times. You know that the Hamiltonian is minus h bar squared over 2m kinetic energy of your oscillator plus some constant, simply written as 1 half omega squared x squared. Okay? So, harmonic oscillator has a kinetic energy and it has a potential energy which is only this here is the operator. These are just constants. Here we have operator square. And obviously the potential looks like this. So this here is the position and the potential is like this. You have solved it, you know what the solution is. My point now is, if we imagine that the kinetic energy was small, okay? So we make this, imagine now only as a thought experiment, we make the first term in our Hamiltonian smaller and smaller and smaller. Okay? This we can do by placing us in a world where we make h bar smaller and smaller and smaller, but we keep this here the same. In the extreme case, where this term here is 0, okay, we know what the eigenfunction of the Hamiltonian look like. Because if you're an Hamiltonian, which is just 1/2 m omega square x squared, the eigenfunctions are the eigenfunctions of the position operator. Because this is the only quantum mechanical operator. Okay? So if we had no kinetic energy, the solutions would be functions which are eigenfunctions of the position operator, so very sharply localized eigenfunction at any point in space. Okay? So we would have for every point in space one eigenfunction, and the eigenvalue would be precisely the value of the potential at that point where it is. Okay? So solving the harmonic oscillator would be very easy without a kinetic energy, and the solutions would be eigenfunctions with a very well-defined position in space. We obviously know that this is not the solution of the harmonic oscillator because of the kinetic energy. So this is now, and I said it is a trivial comment. Trivial comment number one is the role of the kinetic energy is to make the wave functions broader and not like a delta function space. It is to make them broader and give them a more quantum nature. This is also why you have certainly heard many times colleagues of mine saying, in an h bar going to 0 world, meaning a classical world, if you have a general Hamiltonian and you are able to put h bar to 0, then you go to the classical physics because you have well-defined positions like this. You can solve everything, and the quantum nature of your system is given by the kinetic energy. You might say, why is he saying these completely trivial things? But it will be important for us in a minute. Okay? So what we learn is h bar is a measure of how quantum the solution is. Okay. And for h bar going to 0, we have solutions look like delta functions in space. with a very well-defined position. I will use, so you all understand this is completely trivial. You have any quantum mechanical Hamiltonian, kinetic energy plus a potential energy. If you take away the kinetic energy, the solution is well localized in space. The wave function becomes broad and complicating quantum mechanical only due to the kinetic energy. That is clear, no? We will use that in a minute for our real Hamiltonian. But this comment makes sense now only if I put it together with another stupid comment, which you have also seen many times. What happens if we have Hamiltonians as a sum of two Hamiltonians? What I mean is, if you have a Hamiltonian which is depending on some variables x and some variable y, and it has the special form that it's a Hamiltonian h1 of x plus Hamiltonian 2 of y. Why I am saying this? I'm saying this because the big Hamiltonian we have just seen before, it is a little bit like this. There are terms which depend only on variables x, which act on the nuclei, and there are other terms which act only on terms which are electronic, so nuclear and electronic. But in our real Hamiltonian, there is the mixed term. So the interaction between nuclear and electron, there is the one over the distance. So our Hamiltonian does not really look like this. But let us have a look what happens if you have a Hamiltonian like this. So if you have a Hamiltonian which depends on two kinds of coordinates, but you can separate into two sums, h1 and h2, and each one depends only on one kind of coordinates. Well, so in this case, then you can always look for the solution psi of x and y as a product, how did I call it, phi of x times psi of y. Why? So let me show you the proof. If we have h1 of x plus h2 of y times phi of x times psi of y, this here we are looking for gives us an energy phi of x psi of y. No? So this here would be the ground state Schrödinger equation for a system where the Hamiltonian depends on this here. Now I know that the Hamiltonian h1 will only act on phi and the Hamiltonian h2 on psi. So let me write this here explicitly. So this here gives me that I have psi of y times h1 of x acting on phi of x plus phi of x times the Hamiltonian 2 acting on psi of y. And this here is E times phi x. So I've done nothing, no approximation. And now I divide division by phi xi. I can obviously do this only if they are different from 0, but we make this approximation here for a moment. But then I have, so here this Hamiltonian acts on this here, so we get h1 of x phi of x divided by phi of x plus h2 of y times psi of y divided by psi of y is E. I mean, you've seen these stupid things certainly many times. This here we know is a constant. So it does not depend on x or y or whatever. So this is a constant. All dependency on x is here. All dependency on y is here. So since in the end this must be a constant, This means here, since x appears only here, this here cannot depend on x, it must also be a constant. So this here must therefore be a constant. And I call this E1. This here can also not depend on y, because otherwise this here would not be a constant. So this here is also a constant. And I call it E2. And therefore I know that in a system like this, I have that the total energy is the sum of two total energies of two separate systems. And what I have to solve, or what the equation I have, is that h1 of x, phi of x, is E1 phi of x, h2 of y, xi of y, is E2 times xi of y. So whenever you have a quantum mechanical system which depends on two sets of variables, but such that the Hamiltonian is a simple sum of two Hamiltonians, like we have here, then you can, without doing any approximation, always assume that your wave function is a product of two wave functions which each one depend on u1, and you have two completely independent Schrödinger equations which you solve. So this you have certainly seen many times, but it will be useful for us. Okay. So now I have made two, as I said, stupid comments, but why are they useful for us? Because the next step will be to think, okay, on one hand we have here something, when h bar is becoming small, the solutions look like delta functions. But this happens not only if h bar is small, but generally when the kinetic energy term is small. And there's another way how the kinetic energy term can become small, it is if this mass becomes large. And we have seen in our general Hamiltonian there are two kinds of masses flying around. The masses of the electrons are small, but the masses of the nuclei are large. So we can now, in our quest for a solution to our problem, we can say, okay, in those terms where the nuclei degrees of freedom are here, since we are dividing in the kinetic energy by a very large mass, which is at least 1,000 times larger than that of the electrons, we can assume that the kinetic energy term on the nuclei is much less of an effect than the kinetic energy term on the electrons. Okay. In other words, in our total solution to our problem, we can expect that the wave function for the nuclei, because of the small term here, they will not be exact delta functions, but they will be looking much more like delta function in space with a well-defined position than the wave function of an electron. Okay? So this stupid comment tells us, keep this in mind. Probably the nuclear wave functions are rather well-defined in position space, and kinetic energy on them will have a little effect. This thing here tells us we have a complicated large Hamiltonian. We have many terms which depend only on nuclear degrees of freedom. We have other terms which depend only on electronic degrees of freedom. If it was like this, then we could simply solve the electronic problem, solve the nuclear problem separately, and the sum is the sum of the electronic energy plus the nuclear energy. Unfortunately, life is not so easy for us, because we have in our Hamiltonian also a mixed term. The term which depends on electrons and nuclei, which is, as we have said, the important term, the attraction term. Before I have told you, I would not like to neglect it because everything would fly apart. You remember this? Unfortunately, so we cannot neglect the term, but if we neglected it, then we could solve electrons and nuclei separately and we would be safe for many things. So what we will be doing in the next lesson is we try to learn from these two comments. We will try to look for nuclear solutions which are looking like solutions in position space. We will not be exactly like this, but we will keep in mind that the solutions will look something like this. And we know that our total solution will not be a simple product of two wave functions, but will also not be too different from it. Okay? And the challenge of next lesson will be to give a mathematically precise meaning to what I mean by saying it will be close to being a product without really being a product. Okay? So our solution, we know, will not be the product of an electronic wave function times a nuclear wave function because we have the mixed term. but we can look for something which in some well-defined way resembles that. Okay? Because our goal will be, yes, we want to separate electrons and nuclei. Because if we manage to do this, and we have one equation which is only for electrons, then at least we would know that our electronic wave function is a fermionic wave function, and that helps. Okay? So separating electrons and nuclei mathematically helps us then also to get a handle on the symmetries. Okay? So this is our roadmap for next time. Next time, we keep in mind these two stupid comments, apply them to the Hamiltonian, look how we can best of possibly separate electrons and nuclei, and then we continue. Okay? So before I end, I wanted to ask you, does every one of you have either a computer or a smartphone or anything with which you can go to the internet?
Yes.
Which you can bring here in class?
Yes.
Okay, so because I will do something, I don't, have you ever used in a class Socrative? Socrative is a way of teaching where I ask you questions and you answer on your smartphone or on your computer. In this way, you see, I ask questions, you answer, but I do not know who answers what. So it's a way of anonymously asking questions, and then I see what is understood and what is not understood. Okay, so it's quite fun. So next time, and for the future, bring always to your class either your smartphone or your computer, whatever you need to go to the internet. It's very trivial, and I can ask you questions. Okay. So Socrative will be next time. This separation of nuclei and electrons is called Born-Oppenheimer or adiabatic approximation. This all will come next time. Okay. Questions? I switch off now the